In section 2.2, we talked about the graphs of functions, and I'm not going to insult you by going back and making you make tables on your own in order to graph a function. We're just going to use the graphing calculator to do it for us. But there are some functions that you should know without having to graph them. Just have a general idea of what they're going to look like. So, for example, the constant function, which is just a horizontal line. The identity function, which is specifically the line y equals x. And the reason it's called the identity function is because every number that you plug in for x, the same number comes out for y. And then we have our quadratic functions, which are our u's. And you know you're going to have a quadratic function because you're going to have an x squared in the equation. And then we have our cubic functions. Cubic functions generally look something like this. We didn't talk about this, but quartic functions we introduced in Algebra 2. Quartic functions, which are functions whose largest exponent is 4. They generally tend to look like m's or w's. We have our rational function. The rational function often looks something like this. They're hyperbola. They get closer and closer to asymptotes, which they never cross. We have our radical function, which looks like this, also known as the square root function. And remember, these are all functions because not all equations represent functions. We also talked about another one that we've mentioned in the past but didn't really do much with, called the step function. And it's called the step function because it looks like a set of stairs, and also known as the greatest integer function. It says what's the greatest integer between two x values without going over. Those open circles mean that you cannot use that number. Remember, that means non-inclusive, whereas the closed circles mean inclusive. One thing we did mention is that now that we're in pre-calculus, not all of our graphs are going to fit nicely within the window settings that are the default window settings on our graphing calculator. Sometimes we're going to have to change the window settings. And sometimes by changing the window settings, we can get a little bit better idea of what a function is doing and how fast it's increasing or decreasing. So if you graph these three equations, y equals x squared, y equals x to the fourth, and y equals x to the sixth, on the interval -2, 2 by -1, 3. These are your x min and max, and these are your y min and max that you find under the window button on your graphing calculator. You just change them. We're not going to change anything else in the window. The only things we ever usually change are the x min, x max, y min, and y max. And what ends up happening is you see something that looks kind of like this. Y equals x squared kind of looks something like this. Y equals x to the fourth, a little more like this. And y equals x to the sixth. Oh, I should probably, that red one, not as good as I wanted it to look. Looks more like this. And then the y equals x to the sixth looks more like this when you graph it. And kind of what you see happening is that the bottom of the graph, as the exponent gets larger, it kind of flattens out a little bit, and y equals x squared, it was wider on this interval than the other two. So you can probably make a prediction about what y equals x to the 8th will look like without really doing anything. Now let's do something similar, and instead of looking at even exponents of x, let's look at odd exponents of x on the interval -2, 2, -2, 2. Remember, the first interval is for x, the second interval is for y. So when you graph these, y equals x just pretty much looks like it's just a straight line. It's the identity function. I should probably put my little tick marks in here. Y equals x to the 3rd, though, is going to look something like this. Which makes sense because it's a cubic function. We already talked about the general shape of cubic functions. You should already know, if you see x cubed, the general shape of it's going to look like this. And y equals x to the 5th going to look something like this. Now I want you to think about the difference between what these graphs looked like when the exponents were even and what they looked like when they were odd. When they were even, they all pretty much looked quadratic, didn't they? That's kind of interesting. Both ends of the graph were going up. When we use the odd integers for the exponents, one side of the graph was going up and one side of the graph was going down. Keep that in the back of your mind for a little bit. Now let's talk about piecewise functions. Piecewise functions are the ones where you're going to graph a couple different functions, but only pieces of them. Those little inequality symbols next to the function restrict the domain. Now if I do this by hand, if I want to graph y equals x squared, I only want to graph y equals x squared for x less than or equal to 1. So the first value that goes in my table is 1. The rest of the values are going to be numbers that are less than 1. And then I make my table. So 1 squared is 1, 0 squared is 0, -1 squared is 1, -2 squared is 4, -3 squared is 9, and that graph is going to be a ray. The second function, y equals 2x plus 1, I'm going to graph that for x greater than 1. I'm still going to start with the value of 1, but now I'm going to give some values that are greater. So when x is 1, y is 3. When x is 2, it's 5, 3, 7, 4, 9, 5, 10. Now the little inequalities you have to watch out, because the first inequality, x is less than or equal to 1, means that you're going to start your ray at a closed circle. And in the second graph, x is greater than 1 means you're going to start your graph at an open circle. Just like we used closed and open circles on line graphs of inequalities. So now when I go graph this, let's see, I start at 1, 1 with a closed circle, and then I graph 0, 0, -1, 1, -2, 4, and so on and so forth. So the graph looks like this. The red graph goes through 1, 3 at an open circle, and then 2, 5, and then 3, 7, and it's going to go up like this. Now, if you graph this on the graphing calculator, the calculator will not show you open and closed circles. But the way you would type it in is you would put in y1 equals x squared, division sign, parentheses, x less than or equal to 1, close it. This is found under second math, And then it's the test function, and you'll find all the inequality symbols there. And then you would do y2 is equal to 2x plus 1, division sign, parentheses, x greater than 1. And when you graph it, you should get this same exact graph. Now, sometimes it happens that you are given an inequality that looks like this. You can type in that inequality, but the calculator will not graph the function correctly if that's your domain. So what you have to do is you have to change it to this. Very simple. This particular compound inequality is an and statement. The word and is also found under second math, but you arrow one to the right to logic, and you'll find the word and. Now, when you have a compound inequality and you graph it, that piecewise function is not going to be array. This one is going to be a segment, as opposed to these two, which are going to be like rays. The absolute value function is a very interesting function because it's really just a piecewise function. So, if you think about the equation y equals x, and you graph that on the coordinate plane, it looks like this. Well, what happens when I stick absolute value bars around it? That means all the outputs become positive. That means you can't have any negative outputs. It takes this portion of the graph and it basically reflects it over the x-axis. So now you have these two functions. This is the graph of y equals x, but only when x is greater than or equal to 0. And this is the graph of y equals negative x, but when x is less than or equal to 0. Or sorry, not equal, just less than 0. Let's look at a practical application of this greatest integer function, or step function. The cost of a long-distance daytime phone call from Toronto, Canada to Mumbai, India is 69 cents for the first minute and 58 cents for each additional minute, or part of a minute. Draw a graph of the cost, C in dollars, of a phone call as a function of time, T, in minutes. Well, for the first minute, we know that the cost is 69 cents. So that means anything between 0 and 1. So starting at 0, but if you have 0 minutes, you're not getting charged. And 1 being the maximum that you can get the rate is 69 cents. Well, after that, they're going to charge you an additional 58 cents. So from 1 to 2 minutes, it's going to be 69 cents plus 58 cents, which is $1.27. And that's not going to include 1, because 1, you're still going to get at the 69 cent rate. But up to 2 minutes, you're going to be charged $1.27. And then if you're going to go from 2 to 3 minutes, you're going to be charged another 58 cents, which is going to be $1.85. Anywhere from 2 to 3 minutes, and I'll do one more. That anywhere from 3 to 4 minutes, they're going to charge you another 58 cents. So anywhere from 3 to 4 minutes. Now, what would this graph look like when you go to graph it? Well, since you can't talk for negative time, we'll do mostly a first quadrant here. Here's $1, $2, $3. This will be our dollars, and this will be our time t. So we said that from 0 to 1 minute, it costs 68 cents. So something that looked like this. From 1 to 2 minutes, we said it costs $1.27. So something like this. From 2 to 3 minutes, we said it cost $1.85. Oops. Open circle, close circle. And then from 3 to 4 minutes, it costs $2.43. So that would be my step function to represent that scenario. In Algebra 1, we introduced this thing called the vertical line test. And the vertical line test was a way of determining if the graph of an equation represented a function or not a function. So let's say this is a graph, and I wanted to determine if it's a function or not. If you can take a vertical line and you put it anywhere on the graph, and it never touches the curvature more than one time, then it's a function. However, if you can draw a graph and you can take a vertical line and touch more than one location anywhere on the graph, not a function. So things that are not functions. Now we gave you on the notes a whole list of graphs of functions that we want you to know. Well, there are things we've come across so far that weren't functions, like when we studied circles and ellipses. They are not functions. When we studied the sideways parabolas that either open to the left or to the right, they were not functions. When we talk about the graphs of inverse trig functions, they are not functions. How about if you're not given a graph and you're given an equation instead? How can you tell if that's going to be a function or not? Well, it usually happens that if you're given an equation where y, or the dependent variable, the range value, it has an exponent of 1, it's usually going to be a function. So, for example, y minus x squared equals 2 is the same as y equals x squared plus 2, which is basically this graph. It's a parabola that's been shifted up 2 units. Well, those are functions. B, x squared plus y squared equals 4, well, that's just a circle whose center is at the origin and whose radius is 2. Not a function. A lot of times if you have an equation that has an x squared and a y squared, it's not going to be a function. Another way that you can tell it's not a function is if you do this. Let's say you go and you try to solve this for y. Well, you have to square root both sides. And when you do, you end up with this. So these are the two halves of this circle shown in algebraic formation. But you probably know it already as a circle, and circles are never functions. And that should help you out with section 2-2.